Hello. So can you hear my voice?
Yes, I can hear you.
Okay. So can you see my screen?
Yes.
Okay. Right. Mm. By the way, what about this? If I make this one full screen mode, can you see this PowerPoint slide in the full screen mode?
Yes.
Okay. Yeah, that's good. Mhm. All right. It's 10:30. So yeah, let's get started then. My name is Dongyap Na. I am postdoctoral research associate at Purdue now, working with Professor Chu. So on behalf of him, I'm going to deliver a lecture today. Um, Let me make it full screen mode. Oops. Right. Can you see the screen?
Yeah.
So yeah, today we are going to discuss about two important topics. One is frequency domain analysis of Maxwell's equations. Actually, this topic, I think, is very important. That's because it's quite a standard approach in electromagnetic society to deal with the practical problems, but also um, it's gonna serve as a basis for the rest of these courses. So that yeah, deeply understanding these frequency domain concept is very important for the analysis of the scattering or transmission through the medium, transmission of waves through the medium, or field behaviors inside the waveguide and the Green's function, field produced by sources. All kinds of problems, we're going to use this frequency domain concept. And to do this, we're gonna see the phasor technique, which is widely used in circuit analysis. By the way, there are any student who are from different department. I mean, not electrical engineering department. Then yeah, you may be familiar with this phasor technique to analyze the circuit time transient circuit analysis. And the other topic is complex power, and we're gonna derive um, this complex power from the use of phasor technique, and then we're going to see the physical meaning of the real and imaginary part. So let me briefly mention about the fundamental motivation of this frequency domain analysis. We know the Maxwell's equation given here, which is basically the partial differential equations for this vectorial field. I mean, electric field and magnetic field and D and B field all are vectorial field, which are function of space, three-dimensional space, R, and time. You know, and also we have a source J and M here, and actually the EM field obey this Maxwell's equation, so that in order to engineer this state of art communication, wireless communication devices, we need to anticipate the field behavior. That means that we need to solve these Maxwell's equations, but we know that it's very difficult and challenging task. Okay, um, that's because there are a lot of derivative terms ahead of this field, unknown field to be solved. So what we can do actually is that instead of working on this time domain, we move it to the frequency domain, um, and then actually this time derivative partial t can be replaced by just a multiplicative factor j omega, where omega is a frequency. So this is called a phase form of Maxwell's equation. So what we are going to do today is to derive this phasor form of Maxwell's equations. And actually, this Maxwell's equation is for just a single frequency. So at the end, we can use the principle of the linear superposition, just as yeah, linear combination of all the single frequency solution. Then we can finally reconstruct the original solution. So this is the main fundamental motivation of the frequency domain analysis. So yeah, then let's look into the phasor technique. So very um, the the first assumption that we need to make is that, yeah, let's consider the voltage, the arbitrary voltage in the circuit, which is measured at a specific position x and time, and we're going to assume this voltage is time harmonic, meaning that if you look at the figure on the right, uh, just yeah, there are two examples of time harmonic voltage, and let's look into the red dashed curve over x over omega t, just the time. You can see that it behaves like a sine or a cosine, which are called the trigonometric function, and also it is called the time harmonic. That's because it is oscillating in terms of the single frequency, so that um, in this case it has a minus alpha time delay as much as amount of this, and also it has an amplitude. I will call the amplitude v dash. By the way, this is the voltage signal measured at a given position x. So that this time harmonic voltage can be represented by the amplitude times cosine omega plus t. This is the general representation of the time harmonic signal. So what we can do next is that we are going to use the Euler formula, okay? Euler formula, which states that exponential function with the I'm sorry, argument theta is just the cosine theta plus imaginary value of the sine theta. So this is the Euler formula. So so you can see that the cosine omega t plus alpha can be represented the real value of this exponential function. That's because um, so real value of this exponential with the j theta is just the cosine. Okay, and then um, it does not matter for us to move this amplitude term inside this real value bracket. So we have, and also we move this j exponential j alpha term ahead of this exponential j omega t, and we're going to define this term denoted by v under tilde is defined to be the phasor of the real valued voltage signal. Okay, because this exponential factor is complex value, basically complex value, so that this phasor is generally complex valued. So again, this is the definition of the phasor for a time harmonic voltage signal. So this is very simple. So now we can extend this concept of phasor to a vectorial field in the three-dimensional space R and time. For example, electric field. Um, if the electric field behaves time harmonic, then we can represent it uh, in the phasor form here, the real value of the each phasor, also vectorial field, which is complex value, but only the function of space, okay, and the exponential j omega t. Likewise, we can also represent it this time harmonic magnetic field in the phasor form representation, phasor form, and actually these two are fields. And what is M here is that just the magnetic current. Okay. We can also assume that this current is time harmonic. Then we can represent it in this phasor form. And let's substitute these three representation to the farthest law here. Okay. Then this is electric field again, and this is a magnetic field, and this is the magnetic current. So it's just a plugging the phasor form into the corresponding place. Oops, let's sorry. Then we move this curl in again inside the real valued bracket, and also the time derivative term inside the real bracket. And this curl It's just the only the function of space. So it only acts on this complex, I mean, the phasor of the electric field. And this time derivative only acts on the exponential j omega t. That's because it is only the function of time. And then what is that? The time derivative of the exponential j omega t, which is just the j omega exponential j omega t. So that um, so that we can it can be equivalently represented in this way: the real value of the curve, the whole term, and the j omega beta, j omega b field and m field here, and it should be satisfied all t. Okay, so in order to satisfy this condition, uh, just the canceling this time function, time dependence term, and these terms should be same. So just canceling this real value bracket, then what we have is that the curve of the phasor of the electric field should be equal to the j omega times the phasor of magnetic field and a magnetic current. So it almost looks like a original Faraday's laws, in except for the time derivative, which is again can be replaced by j omega, which is just a multiplicative factor. This is the Faraday's law, the phasor form. We can do the same thing, same procedure. We can perform same procedure to derive the rest of Maxwell's equation in the phasor form. Okay, um, meaning that we can represent just the original field in the phasor form, and then plug to the corresponding Maxwell's equation, and then derive this phasor for Maxwell's equations. So are there any questions so far? Okay, so again, this is for the time harmonic signal, just a single frequency. So actually, it turns out that this phasor is not only function of the space, it should be function of omega. That's because if we look at the Maxwell's equation here, actually d uh, d is related to the electric field through the medium permittivity by the constitutive relation, but this epsilon can be function of omega as well as the function of space, so that this phasor actually function of the both function of space and frequency. Okay, so yes, all the phasors are actually the function of space and frequency. And then Maxwell's equations has a distinct property, which is linearity, meaning that let's say this is a solution of Maxwell's equation E sub A. This is our another solutions of Maxwell's equation. Let's say this is EB, and each linear combination, just the scaling EA, one solution plus scaling EB, their summation is also solutions solution of Maxwell's equation. So this is a linearity of Maxwell's equation. So that it means that if we combine if we combine solutions at different frequencies, meaning that let's say this is our solution at a certain frequency, let's say omega 1. This is one solution, and another solution at different frequency, and their linear combination. Each linear combination is gonna be also a solution of Maxwell's equation. Okay, so the we can generalize this concept of linear combination just a mention to the integration over frequency. Uh, so this is again this time harmonic field solution in the phasor form. And then we can do the linear combination with this integration. Then we have a general solution for electric field. So I'm not gonna cover some details about this Fourier transform representation. You can um, you can look into the lecture book, maybe updated today. It's very similar. It's very similar to the phasor technique. So then you can look into that lecture book. So uh, then next topic is yeah, then this is the overview of the frequency domain analysis again. So because it is difficult to solve this original Maxwell's equation due to the time derivative interwound with mixed with the spatial derivative term, so we can reduce the complexity of the problems by assuming that fields are time harmonic. Then um, we can represent all the field in the phasor form, and then we can do the math to prove that this time derivative can be replaced by this j omega, which is just multiplicative factor. Then we can, by solving this phasor form of Maxwell's equation, we can obtain the phasor solution of each field, and then we can use the linear superposition principle of the linear superposition to reconstruct the original solution. Okay, this is the overview of the frequency domain analysis. Typically, for the again for the rest of these courses, instead of dealing with this complicated time varying electromagnetic field, we're solving this phasor form Maxwell's equations. Um, okay, any questions? Maybe, yeah, you're familiar with this phasor technique concept from the circuit theory, so it's not gonna be too difficult. So you may need to be familiar with this conversion between this time and the frequency domain um, of this course. And then let's move on another topic, which is complex power. So the power, what is power? Power is measured in watt. And in the circuit theory, we know that the power is defined by the voltage times the current. So it's kind of the energy. the time, the ratio of the energy carried by electrons in the circuit. On the other hand, we can generalize this concept by replacing the uh, voltage to electric field and current to the magnetic field. And also, these are vectors, so we can, it's just a scalar multiplication, but it's gonna be this cross product. Then the product between electric field and magnetic field is defined as Poynting vector, or it is just a uh, but it is called a Poynting vector. The power density carried by this electromagnetic field. And also, if we observe the dimension of these two quantities, electric field is measured voltage per meter. Uh, H field is measured amperes per meter. So the resulting dimension is going to be watt per meter square. So it's a power per kind of surface. So I described how much the power is flowing out of the surface. Okay, it is the concept of the Poynting vector or power density. So it might be good to observe this figure on the right. We have a battery. It's kind of circuit. So it's kind of circuit flowing. Um, we have a battery here, and the load, the current is flowing like a clockwise direction. And we know that if we have battery like this with the plus and negative polarity electric field, illustrated by a red arrow, should direct from the plus and minus polarity, so that it should direct from top to bottom, and the current is flowing from bottom to top. This is current. So that by Ampere's law, or you can use your right hand rule, then the current should flow, the magnetic field should should be induced from this current, like um, counterclockwise here, illustrated by red, I mean green arrow here. Okay, so based on this equation, we can also use the right-hand rule to see the direction of the Poynting vector or power density. So we can use our right-hand rule from electric field to magnetic field. Then we have direction of the power. Um, we can see that power is coming out of the battery with this blue arrow. That means that this battery is pumping energy from inside the battery to this circuit. Okay, and then the current is flowing uh, in this direction. We can observe the magnetic field. Let's say on this cross section P, magnetic field, illustrated by this green arrow, should direct in this way. Okay, the voltage drop still, electric field should direct from the plus and minus polarity. So this is going to be electric field. And you can also use your right hand to measure the direction of the power flowing. In this case, the power is moving from the left to the right. Okay, and then finally at the load electric field this way, and due to the fact that currents flowing from the top to bottom, then the magnetic field should be clockwise, and then we can see that the resulting power is going from, power is directing toward the load so that the power is absorbed by load. Actually, this is very intuitive. I mean, very intuitive to see the how the power is flowing in this circuit according to the direction of the voltage and current. So we are going to uh, derive the complex power or complex Poynting vector. So again, we assume that the electric field and magnetic fields are time harmonic, so that we can use the phasor representation here. And this is the phasor, and real value that this whole thing reconstruct the original time harmonic uh, electric field. And then we can let us substitute this representation to the Poynting vector. Actually, this subscription in meaning the instantaneous Poynting vector. So it changes over time. So then instantaneous power is gonna be just a cross product between two phasors, and then so from this to this equality, we can use that. Let's say this is an arbitrarily complex value, so that the real value of the complex value, let's say the complex value is the is real value plus the imaginary value, so that the real value of the complex is just the 1 over 2 original complex value plus its complex conjugate. The complex conjugate is the a minus jb, so that their summation is going to be 2a, so it recovers the original the real value of the z. So we have used this identity, the real value of the electric field, its original form plus its complex conjugate here. The same thing for the magnetic field. And then let's expand summation of these two terms. Then we get like a four terms. I mean, this term, cross product between these two terms is going to be E cross H exponential J 2 omega T. Likewise, we have the rest of terms. It is interesting to observe that the first and fourth has time dependence, exponential J 2 omega T, and also their complex conjugate. If you closely look at these two terms, they're basically complex conjugate. And also on these two terms, second and third, they don't have the time dependence term. That's because this and this exponential j omega t can be canceled out, and also their complex conjugate as well. So we used, in this time we can use this identity the reverse way to represent like in this way. So the real value of this first term implicitly account for this fourth term, and also the real value of the second term and the third can be represented the real value of the second term. Okay, so then this is the instantaneous Poynting vector, and then what we do next is to time average this instantaneous power density. Actually, the time average is defined in this way. Uh, uh, for arbitrarily time signal, we can integrate it over 0 to t, capital T. Capital T may be the 1 over omega, just the period of the time harmonic signal. Then divide by t for the normalization, then take the limit. Okay, so this is the time averaging process. It is denoted by this bracket here. So if we do this time averaging process, we do not have any time dependence no longer, so that this is the um, time averaged instantaneous power defined in this way. Then let us substitute uh, let me just erase this. Let us substitute this expression to here. Okay, yeah, just the time integral. Then uh, we can see that the first term has time dependence, but the second term does not. So this term actually canceled out because yeah, we have assumed that the uppercase t is 1 over omega. So by the property of the exponential function or the sine and cosine function, we can prove that the first term is canceled out. So we only have the second term when we do the time average that for the instantaneous power density. So if we define the cross product between the phasor of the electric field and magnetic complex conjugate of magnetic field as um, complex power. Okay, so this is gonna be just the real value of this complex power. So what that means is that the real part of the complex power is just the time averaged power. Okay, what is the time averaged power? That is the power consumed in load in the circuit theory or in electromagnetic field, which is power carried by field, electromagnetic field, from the source to the ambient space. If we consider the antenna, then let's say this, we can model like an antenna radiating field through the space. We can model it like this circuit by using the circuit schematic. So antenna is kind of source, and then the space is kind of radiation resistance, so that the power is carried to the space or consumed in load, radiation loss. And so yeah, this is the complex power, and we know that each real part corresponds to the time average of power. Then what is the physical meaning of the imaginary part of it? In order to understand it, it's better to revisit the circuit theory and conclude. Actually, from the circuit theory, we know that the imaginary part of complex power is reactive power. Reactive power is unused power wandering around in a circuit. For example, if we have an inductance in our circuit on top of the just the real valued resistance, then some portion of power is not consumed, but due to the inductance, but it's just um, it can be resonant in the circuit, just wandering around in a circuit, and also in the electromagnetic field, this reactive power exists. Um, for example, um, in the last page, I showed you the example of the antenna. Maybe better to see this picture. So we have antenna here, and we know that the field, I mean, we have antenna on our cell phone, and for any purpose of the wireless communication, we should have antenna. Antenna generate field, and we can model like this antenna system as again this voltage signal and kind of resistance. This is kind of radiation resistance. Okay, so that the power is consumed in this resistance. That means that uh, the power, some portion of power, is radiated from the source antenna to the free space. It takes the form of radiation. On the other hand, very near, very close to this antenna, some portion of power does not radiate, but it is resonant and close to antenna. Energy transfer, energy can be back transferred from space to the antenna. Actually, this kind of phenomenon can be modeled by some capacitance or inductance component so that the power is not used and just wandering around this circuit, and physically it models the energy firstly generated from the antenna but does not radiate, but it resonates somehow and then it goes back to the antenna. So this kind of power is the reactive power, closely related to the imaginary of the complex power. Okay, but this radiation is closely related to the time averaged power, which is a real valued power. Um, Again, this reactive power happens whenever we have the phase delay between the voltage and current in our circuit. If we don't have any reactive component, for example, inductance or capacitance, if we only have the resistance in our circuit, then we don't have any reactive power. Uh, there are um, maybe you can see the details in the lecture book, just the math, how time average power and the reactive power is related to the complex power. So, are there any questions so far? No.
I have a question real quick. Will this slide deck be available to us?
Yeah, 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 of course.
Okay, thank you.
Hmm. Actually, all the equations came from like Professor Chu's lecture book here. Can you see my PDF screen? You can only see my PowerPoint slide. Actually, I open PDF window, but can you see?
No, I can just see the PowerPoint.
Okay. Yeah. The thing is that um, all the math comes from the professor's lecture book. So maybe you can, yeah, you can see my PowerPoint slide, lecture note or lecture book. Professor Chi's lecture book doesn't matter. Mm. Uh, Another questions? Or- Okay, just let me go over them because I have a few more minutes. So, yes, again, in order to reduce the complexity, we have actually we have discussed about frequency domain analysis and the complex power, and this concept is again very important um, for the rest of these courses. We're gonna deal with maybe after these courses we're going to discuss about constitutive relation more in detail, um, meaning that the epsilon relate electric field and electric flux density in the frequency domain, um, and also we're going to see some scattering effect from arbitrarily, some single layered dielectric media. So meaning that if there is a incident field, how it's scattered and transmitted. And all kinds of analysis, we're gonna adopt this frequency domain analysis, okay? For a time harmonic signal, we're only dealing with the phasor of this field. And also the waveguide problems and the Green function. Yeah, we are just based on this frequency domain analysis. So maybe you may need to be, yeah, get familiar with this concept. The essence is that we are replacing this time derivative term uh, by this j omega term. By the way, uh, by the way, we assume that this partial t was replaced by j omega. On the other hand, if you look at some articles, the physics society, just convention that they replace this time derivative as a minus I omega. But in the electrical engineering society, we often use J omega, but the physics society, they use the minus J omega. Um, Actually, you can derive minus I omega t by replacing yeah, these terms with this just convention. But note that we are mostly using j omega t time convention. Um, yeah, so we first assume that these fields are time harmonic, oscillating with a single frequency, and we could have represented them in the phasor form like this way. And then if we substitute it to the Faraday's law by do the some math, we arrive at this Faraday's law in the phasor form. Again, the time derivative is replaced by this j omega. Uh, so we have Maxwell's equation in the frequency domain. Okay. So this is just a solution for single frequency. We can use the principle of the linear superposition. We can describe arbitrarily field, just non-time harmonic arbitrarily field, again by using the linear superposition of all the single frequency solution. Okay. Um, and the other topic that we have discussed was about the complex power. We're starting from this Poynting vector. Instantaneous power density is defined by cross product between electric and magnetic field, vectorial field. Then we substitute this phasor form of electromagnetic field into the instantaneous power density by doing some math. We can arrive two facts. One is that the time averaged instantaneous Poynting vector physically no this time averaged Poynting vector correspond to the real value of the complex power. Complex power is defined the cross product between the phasor of the electric field and complex conjugate of the magnetic field. Okay, and what was the real imaginary part of it? Physically, it means the reactive power. It's not used power in the load, but just it can exist in the form of the resonance in a circuit due to the reactive component, particularly when it comes to the electromagnetic field. It can be it models like some energy firstly generated from antenna but not radiated, but it transfer back to the sources. Okay. Okay. Other questions? Otherwise, yeah, we can stop here. Okay, if you don't have any questions, we can stop here. And yeah, thank you for joining the lecture today. Okay, let me see. So are there any limitations to assuming purely time harmonic? Is there John here? No? Oh. Johnson. Okay, we can stop here. Yeah. Thank you. Bye-bye.